Hello everyone, and welcome to this video titled Continuity. So in this video, I'm going to be taking you through a preview version of the Knewton Alta assignment that is also titled Continuity. So please understand that this is a preview of the assignment. So that means that questions I work on in this video may not be the exact same questions that you work on when you work on the assignment yourself as a student. But the objectives are the same, and the way I would go, that you would go about working on those problems will be the same. So hopefully watching through these will help you when you work on them on your own. All right, so here we are at Knewton Alta. The look of an assignment. You won't see the word preview, right? You'll just have the title of the section. And in this particular course I'm working in, it's section 2.4's homework called Continuity. In the upper right-hand corner, you should see a mastery bar. It tells you how far along you've gotten in the assignment. Next to that, an activity log. Click on that, and you can see all the objectives. So this assignment here has 6 objectives, broken up into 2 parts. There's continuity at a point. So we'll have to run through these 3 objectives first before moving into continuity over an interval and the intermediate value theorem. And we'll run through those 3 objectives. Now I could, if I wanted, hit the start button on this other section and go through the other section's objectives first, but I'm not going to do that. All right, then you have your current objective. Then you can switch, sections like I told you. You can switch parts of the assignment. And then the question beneath it, related to that objective. And this one is, just a multiple choice one. Some are multiple choice, fill in the blank. There's different varieties of question. And then at the bottom of every question, you should see a feedback button. So if you happen to notice any typographical errors or errors in the question, errors in the answer explanations, you can send feedback directly to Knewton support, and hopefully they can get back to you soon and help you in some way. Now, the instructor cheat button, of course, is only for instructors. You will not see this as a student. This is just for demonstration purposes to fill in answers really quickly. I will not be using this in this video. And then you will have a more instruction button. All right, so if you're on a particular objective or a question and you don't remember what you're doing, or you don't remember the material very well, you click on more instruction and then open instruction related to that particular objective. You'll get some reading or videos or both, and hopefully that'll help you get through whatever question you're working on. Okay, so here in this first question, I'm on the objective, explain the 3 conditions for continuity at a point. So I will discuss those first, and we'll come back to the question. So this is on continuity at a point. So here's how we define continuity at a point. So a function, say y equals, and I'll just call this function f. So f of x is continuous at a particular value. So at, say, x equals a when, and then the following three conditions must hold. So that's why in the objective title it was explain the three conditions for continuity at a point. So the first condition that needs to be met for a function to be considered continuous somewhere is that the value of the function at a must exist, right, must be defined, right? As if you were to plug in a for x and it didn't exist or it wasn't defined, then there's no point in talking about being continuous there. And second condition, the limit as x approaches a of our function. So remember what this meant, right? This was what happens as x gets closer and closer to a, but without becoming a. So this is two-sided. This limit must exist as well. Right? Must exist. So if this limit, this two-sided limit does not exist, or is infinite in some fashion, then we can't say a function is continuous at a. And finally, the third condition is that the limit as x approaches a of the function is the same as the value of the function at x equals a. So these two are equal. So the limit as x approaches a of the function is equivalent to the value of the function at a itself. So graphically speaking, here's what's happening. At x equals a, when a function's considered continuous there. So here's the xy plane, and here's x equals a on the x-axis. So the first condition is the value of f at a must be defined. So there's got to be a point on the graph. So here's a solid point with a for the input, f of a for the output. So I'll put that as the y value over here, f of a. Then the second condition says the limit as x approaches a, from both sides must exist. So remember what that meant. That meant that from the left side, approaching one location, a specific location, and from the right side, approaching that same location, that same point in the plane. And then putting it all together in the third condition, the two-sided limit must be this f of a value, right? So this point I just plotted, this last statement here, this last condition means that the graph, from the left side of a and from the right side of a is approaching that location where x equals a and the output is f of a. Now, another way I've seen this interpreted or described is, you can draw the graph without lifting your pencil. Seen it described that way, right? If I was drawing this at around x equals a, so I'm coming in from the left here, and then at x equals a, there's a solid point, so I don't need to lift my pencil, and I can keep drawing it. All right, so that continuity. So if not, all right, if any of these conditions fail, if any of these three conditions are not met, then the function is called discontinuous at x equals a, right? Or it is not continuous. And later on in the video, we'll talk about there will be objectives on discontinuities. Where are there breaks or holes or jumps in the graph? But here, when you are continuous, there's no break, there's no hole, there's no jump. It's one connected piece. Okay, so this first question, we're given, a piecewise defined function. F of x equals, you got the square root of 3x plus 2. That is only when x is between negative 2/3 and 1, but not including negative 2/3 and including 1. And then the output is 3x squared plus 3x minus 6 plus the square root of 5, but only when x is greater than 1. Okay, so we're asked to determine which of the following statements about the continuity of f at x equals 1 are true. So I'll write this function up and go through those three conditions at x equals 1. So our function, again, was piecewise. The way you calculate the output changes depending on the input. Got the square root of 3x plus 2. But that's, only if x is between negative 2/3 and positive 1, not including negative 2/3, but including, you have the or equal to here, positive 1. And then the other piece, f of x, the output is 3x squared plus 3x minus 6, and then plus the square root of 5. All right, that output, but only if, x is greater than 1. So let's go through the conditions. So the question is this function continuous at x equals 1? All right, so that's the big question being asked here. Go through all three conditions. So the first one, let's see what happens. Do we get an actual value of f when x equals 1? And yes, we do. Okay. When x equals 1, I'm plugging into this piece up here, and I get the square root of 3 times 1 plus 2. So it's the square root of 5. So check, right? The value of the function is defined at x equals 1. Right? And so if I were to go look at a graph, and I'll go to desmos.com in a minute, you can take a look at this. But so when x is 1, the output is positive square root of 5. Right? So I have this location is on the graph of this function. Solid point. Right. Part 2 is we want to take the limit as x approaches 1 of the function. Now with the piecewise defined functions, remember this is x is not equal to 1, right? X is approaching 1. And if we approach 1 from the left, plug in values less than 1, we have to go into this top expression. But if we plug in values to the right of 1 or greater than 1, we have to go into this bottom expression. So I'm going to look at the left side and right side limits separately and see that hopefully they are equal. So left side, we got the limit as x approaches 1 from the left. Again, this means that I'm plugging in values of x less than 1. And so my function has an output of this expression, right? That one where x is less than 1 up here. Square root of 3x plus 2. And since 1 is in the domain of this, I can apply the limit laws and just do a direct substitution. And this would again be the square root of, 3 times 1 plus 2, the square root of 5. So this is telling me that if I were to graph this, and again I'll show you a graph later, that from the left side of 1, it might be coming from above. I'm not being super specific about this right now. But from the left side of 1, the graph is approaching this location with 1 comma square root of 5. So far so good. But to be continuous at x equals 1, it's got to do the same thing on the right side. All right, so let's look at the right side limit as well. So the limit as x approaches 1 from the right, little plus sign there. Remember, this means x is greater than 1, so I'm on this bottom piece. So the expression I'd be going into is 3x squared plus 3x minus 6 plus the square root of 5. Now, being that this is a polynomial, 1 definitely is in the domain of this, so I can apply the limit laws and just do a direct substitution here. This is going to be 3 times 1 squared plus 3 times 1 minus 6 plus the square root of 5. Well, this is just 3 plus 3, which is 6, minus 6 is 0, plus the square root of 5. This is just the square root of 5 again. So we do have continuity, right? From the left side of the graph, again, it might be coming from above or below. I'm just saying this tells me that from the left side and the right side, the graph is approaching this location with the point, 1 comma root 5. So the two-sided limit is existing, and it has the value of the square root of 5. And then the third condition is that, these must be the same, right? So the third condition is that, the two-sided limit, so the limit as x approaches 1 of our function, has the same value as f at 1, right? Which, again, both of these, so we're the square root of 5. So check, 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 right? The function is defined at 1. The limit as x approaches 1 from both sides exists, and they are the same value. So the answer to this question is, yes, f, this particular function we are given, is continuous at x equals 1. Right? So if I were to draw it, you go through that point, without lifting your pencil. All right, so I'm going to go to Desmos and show that, verify that this is true, that both of these pieces meet at the same location. So I'm at desmos.com. Now, I'm just going to graph one piece at a time, just to show you how they connect. So on the left side here, you can enter the expression for the top piece, which was the square root of 3x plus 2. But I only want the part of it, so in curly braces, I only want the part of it that's between negative 2/3 is less than x is less than or equal to 1. Right, so just that part of it right there. That is it. Now you see how it ends at the point one. Now that's 2.23607. That is the point 1 comma square root of 5. I'll have that, I'll label that. So yeah, so you see that point 1 comma, 2.3607 is there. It is solid, and the graph, is approaching that location from the left. And then the right piece, right, so in parentheses, here is the expression for the second piece, 3x squared plus 3x minus 6 plus the square root of 5. But I only want to look at this, or I don't want to look at the whole parabola. I just want to look at the part of it that has x greater than 1. And do you see how from the right side, it's still approach now on the right piece, it is undefined, but you see how it's filled in by the left piece? It is solid from the left piece. So if I go to draw this thing, it's totally connected. All right. They are connected at this solid point, 1 comma the square root of 5. So my drawing wasn't great, but still I pointed out the fact that they do connect. So this function can be drawn without lifting your pencil at x equals 1. So back to the homework problem. Let's see, f is not, you just choose the correct answer below. So f is not continuous at x equals 1 because it's not defined at x equals 1. That's false. We saw it was the square root of 5 at x equals 1. F of 1 exists, but f is not continuous at x equals 1 because the limit as x approaches 1 of f does not exist. Well, we saw that wasn't true either. The two-sided limit did exist and was, the square root of 5. So both of these exist, but it's not continuous because they're not equal. Well, again, that was also false. The two-sided limit, as x approached 1, and the value of f at 1 were both the square root of 5. So we can only conclude that, and you saw it in the picture, the graph, that f is continuous at x equals 1. All right, so then I'm going to hit submit once I've chosen an answer. And if you get something correct, it'll say, hey, that's right, give you a little green banner here, give you some encouraging words. And whether you get something correct or incorrect, it will always have an answer explanation afterwards. I would highly suggest, looking these over. If you got it wrong, definitely look these over so you can hopefully figure out why you got something wrong and maybe fix your mistakes or learn from your mistakes for future questions like this. And if it's correct, you might still want to look over the answer explanations. Maybe you did the problem in a very roundabout way that was very long and boring and tedious, but then you read through the answer explanation and they do it in a much more efficient, much quicker way that you like better. And, might keep note of that and try it out for the next question you see that's like that. All right, so let's continue on. All right, so it did the objective switch on me. It does that interleaving. All right, so I did one question, made a little progress in this objective. So now I moved over to distinguish between the 3 kinds of discontinuity. All right, so back to explain what those are. All right, so I had up what continuity at a point meant. All right, so back here, this is what it meant to be continuous at x equals a. And the value existed at a, there was an output. The two-sided limit exists at a, they're approaching the same, the graph is approaching the same location from both sides of a, and these two values are the same thing. Well, if any one of these fails, then we say, the function's discontinuous at x equals a. So what you're doing now saying, hey, if one of these fails, what kind of discontinuity do we have? So they actually classify the discontinuities. They call them, a certain type of discontinuity. All right, so the types of discontinuity or kinds of discontinuity. And in this particular text, there are three. There are more than three. I'll say that right now. Um, discontinuity. But we're just going to go over, the main three that are usually covered in a Calculus 1 class. All right, so the first one is called a removable. Discontinuity, and this is where you have your just a plain old one missing point. This is where you have a hole in the graph. So when you have these, this is the limit, the second condition is met. So the two-sided limit exists, but is not equal to the value of the function at a. Oh, sorry, I put a there. Sorry. This should be the limit as x approaches a of f of x, not f of a. But it's not equal to the value of the function at a. Okay, so graphically speaking, we could have the two following scenarios. So here's a xy plane, here's x equals a. So the two-sided limit exists, meaning that from the left of a, some location, I'll make an open point there, that location is approached. From the right side, same location is approached, but then the value of f at a is maybe some other value. Maybe the point's up here. Here's a comma f of a. Not filling in the point. So if I were to draw this, I'd have to lift my pencil at A, go fill that point up there, and then come back down, So just a hole in the graph. Now, here, f at A exists, but it might not even exist. So same kind of picture here, where left side limit, left side of the graph approaches some open point, some location. Right side approaching that same location. All right, so again, there's just one hole in the graph, and maybe f of a is undefined. That could be another scenario, right? So if x equals a makes the expression undefined, you don't even have a point there, and you can't talk about being continuous. So if I were to draw this, I'd have to lift my pencil and, I miss a point and continue on. So again, discontinuity. Call that removable, just one popped out point. All right, the next type that I'll discuss that you'll be seeing is a jump discontinuity. All right, so this is exactly as it sounds, where you're drawing it and then have to lift your pencil and jump up or down to some other point and then continue on. So there's definitely a break in the graph. Now when this happens when the limit as x approaches a from the left and the right both exist. So each one-sided limit exists, but they're not equal. So the two-sided limit would not exist. Remember, D and E for does not exist. So again, they're not equal. So graphically speaking, you're going to see a jump discontinuity, at x equals a when this happens. So again, say the left side limit, left side of the graph to the left of a approaches a particular location, and I'll make it an open point. And the right side also approaches a location, but it's a totally different location. So can you see why they call it a jump? If I'm drawing this, I have to stop here, jump up here, and then continue on. I still have to lift my pencil. Now, one of these points could be filled in, but they don't have to be, right? You just approach one location from the left of A and a totally different location from the right of A. You have one of these jump discontinuities. And finally, the only other kind they're going to talk about, again, there are more, but we're only going to discuss three, is you have your infinite discontinuity. So this is where you have a vertical asymptote. So you may recall in an earlier video on limits, a vertical asymptote will be at any value where either side is going to some kind of infinity. So the limit as x approaches a from the left of your function is, positive or negative infinity, or the right side, limit as x approaches a from the right of the function is positive, one of the infinities, or both, right? But as long as one of these, if either side is infinite, some kind of infinite limit, then we'll call it an infinite discontinuity in this particular text. Right, so here's x equals a, so again, you don't have to do it from both sides. I'll put in a little asymptote line, a little dotted line there. So say from the left, graph's going to, positive infinity going up forever. Now it could approach an actual point to the right. Maybe there's AF of A right there. But as long as one of the sides, so left side or right side, as long as at least one of the sides of A, the graph is going to some kind of infinity, going up forever or down forever, you definitely have a discontinuity, and they'll call it infinite. And you can clearly see that there's a break in the graph here, right? I'm going draw, 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 left up forever. I would have to definitely lift my pencil and come back down here to draw the rest of it. So, again, both sides could go to infinity, but again, as long as one of them goes to infinity, some kind of infinity, discontinuity, infinite discontinuity. All right, so back to the question. So, we're given this function here, and once again, we have a multiple choice. All right, select the best answer. So we're given this rational function, right? You got polynomial divided by polynomial. And we're asked, which of the following statements are true? So you notice all these statements revolve around being continuous or discontinuous at x equals 4. So I'll write the function up and we'll go through, again, we'll go through the conditions of continuity, those three conditions. So our function and numerator is negative 2x squared plus 20x minus 48. Denominator x minus 4. And then, again, the big question is f continuous at x equals 4? All right. Well, first condition, can I even plug 4 in? Well, if you do, the numerator, you'd get this. If I plugged 4 in for x, this would be -8 plus -80. Oh, sorry, not -8. 4 squared is 16 times -2 would be -32, and minus 48 would be -80 plus, and then 20 times 4 is 80, so you get 0 in the numerator, which is fine. You can have 0 in a numerator, but then the denominator is the problem, right? 4 minus 4 is 0. So can't divide by 0, can't have a denominator of 0, so this is undefined. All right, so the answer to our question is no. That means f is discontinuous at x equals 4. So now the question is, what kind of discontinuity do we have? So let's see, let's now remember the removable and the jump and the infinite, they all depend on the limit, what happens as x approaches 4. So I'm going to take that. Now the limit, let's take the two-sided limit here. Limit as x approaches 4 of our function. Now you already saw me plug in 4 here. If you assumed, hey, I'm just going to use the limit laws and make a direct substitution, that's a problem. Remember, this 0 divided by 0 was nonsense, meaningless, right? This tells me nothing. They called that an indeterminate form of a limit. So you may recall in the video on the limit laws, in that 0 divided by 0 case, I had to algebraically manipulate the expression, rewrite it in some way to where I could apply the limit laws and make a direct substitution. So this fraction here, just simplifying a fraction. So I'm going to factor out, I'm going to factor the numerator. The denominator can't be factored anymore. I'm going to factor the numerator and then, cancel any common factors with the denominator. Now that numerator, if I pull out -2, and I like having a lead coefficient that, all these have a common factor of 2. So I'm going to pull out -2. Then we have times x squared minus 10x, then plus 24, divided by x minus 4. And again, I'll put that in parentheses because it doesn't factor any further. That's the only factor in the denominator. And then I'll factor the numerator, right? We got -2 times, and then this quadratic factors to x minus 6 times x minus 4. And right? You're seeing now, I can do some canceling here, right? X is not 4 in this, right? We're approaching 4. And if x is not 4, then this x minus 4 and this x minus 4, those are the same non-zero number. And when you divide, the same non-zero number by itself, you get 1. So my limit here is equivalent to the limit as x approaches 4 of, and then what's left over after simplifying, this -2 times the quantity x minus 6. Now I have an expression where I can apply the limit laws and just do a direct substitution. If I plug in 4 for x, 4 minus 6 is -2 times -2, +4. So what's happening in the graph of this thing is that as x approaches 4 from both sides, y is approaching 4 as well. So you have this empty point, this hole with coordinates 4, 4, and the graph is approaching that location on both sides, right? But there's still the discontinuity there. And I'll show you in a graph. So this is removable. Remember, when it's just a hole, right? This two-sided limit exists, but it's definitely not the same as the value of the function at 4, because that's undefined. We have a removable, right? So f has a hole, a removable discontinuity at x equals 4. And that's what I'm going to answer. Now, I'm also going to go to Desmos, put this in, and we'll see that. Now, you don't see it right away. You actually have to go click on the point. So here's, the function we were given. Make sure your numerator is, in parentheses so that it's all up there. Negative 2x squared plus 20x minus 48 divided by x minus 4. And it looks like the graph of a line, right? Now look, I know you can't tell that there's a hole there, because there's infinitely many points. It's very dense. But if I click on the graph and scoot over to where x equals 4, you're going to see that hole show up. See 4, comma, undefined. So there's a hole missing 1 point. So again, a removable discontinuity. So back here, that's what I'm going to answer, right? F has a removable discontinuity at x equals 4. Submit. Hooray. And don't forget to read through the answer explanations. All right, so more continuity, but this time, with a, now we already did one like this earlier, actually. They gave us a piecewise defined function and asked us if it was, continuous or discontinuous at a certain value. So this one's just a graph, though. All right. So you are asked to determine the intervals over which the function shown below is continuous. And you're entering your answer in interval notation. Use a comma to separate multiple intervals, right? So this is just go left to right on the x-axis. And where is the function continuous? And then just make sure to exclude values where it's discontinuous, right? So I'll point out where this is discontinuous, right? Can you see that we're continuous, continuous, continuous from, negative infinity? This little arrow means to the left forever. So from negative infinity up to, negative 3. So you see at negative 3, there's one of those removable discontinuities. So that's the first interval I'm going to put. So parentheses, negative infinity. And you should, now if they don't have the infinity symbol, you gotta change the menu. I think basic has it, yeah. So from negative infinity up to negative 3, but not including negative 3, so parentheses on the negative 3. Now instead of the union symbol, they asked you to separate the intervals with a comma, right? So I'm putting a comma next. All right, then keep moving left to right. Then from negative 3 to 0, I can continue graphing, without lifting my pencil. So we're continuous from negative 3 up to 0, but, not at 0. There's clearly a jump discontinuity at 0. So from x is negative 3 to x is 0, but not including negative 3 or 0. That'll be the next interval over which this function is continuous. So again, just parentheses around those, right? And then a comma for the between the intervals. All right, then from 0 to 3, right? So from x equals 0 to x equals 3, you're drawing more and more of the graph without lifting your pencil. So this function's continuous between 0 and 3, But then at 0 you have that jump discontinuity, and at 3 you have one of those infinite discontinuities, right? It's implied that we're going down forever on both sides here. So from 0 to 3 is my next interval. So parentheses 0 to positive 3, and then comma, and then finally, again going left to right on the x-axis, you see to the right of 3 from 3 onward, but not including 3, not at 3, the graph is, continuous. The function can be drawn without any breaks or holes or jumps or gaps. So then my last interval, parentheses from 3 to, and then just infinity. You could put plus infinity, but I'll just put infinity and close the parentheses there. For all these x values that I've just described in interval notation, the function is continuous. All right, so it's basically everywhere except where there's a removable or a jump or an infinite discontinuity. And I'll hit submit. Wonderful. So that one's not so bad. You're just looking at a picture. You have to do a lot of writing there. All right, so back to explain the 3 conditions for continuity at a point. Now here's another one with just a graph. So I'm just going to explain this one, right? There's not a whole lot to write here. Just look at it. So they're saying the graph of f is shown below. Which of the following statements about the continuity of f at x equals 0 are true? So remember the first condition was, does f have a value at x equals 0? And yes, it does. You see how the point 0, 0 is there? So it is defined at 0. So this first statement is not true. I'm not selecting that one. It is defined at 0. There is a solid point here. And f of 0 would be 0. Input 0, output 0. Now the second condition is the one that fails. Right? Remember the two-sided limit had to exist. So the left side and right side had to be the same value. Well, you see to the left of 0, I'm on this piece, and that's approaching this location down here with a y value of -6. So the left side limit is -6. But to the right of 0, you're approaching the origin with a y value of 0. So left side limit is -6. The right side limit is 0. So the two-sided limit does not exist, right? So that is the problem. And you have one of those, jump discontinuities where the left side exists, the right side exists, but they're not the same. So that is this second condition. F of 0 exists, right? The value of f at 0 is 0, but it's not continuous there because the two-sided limit does not exist. Okay, so that's it. Why is this discontinuous at x equals 0? Great. All right, so another graph. How nice. So again, here's another graph of a function. Which of the following statements are true? So this is definitely, got a jump discontinuity at -6, right? Got an infinite discontinuity at 0, a vertical asymptote. And looks like that's the only place where there's discontinuities. So yeah, jump discontinuity at x equals -6 is the only one that is true here, right? At x equals -6, the left side limit is -4. The right side limit is +6, right? So the left side limit exists, the right side limit exists, but they're not the same. So you had that jump, and you can clearly see the jump in the graph there. Great. All right, so now we're not given a graph. We can make one. If I go plot each piece in Desmos, but I'm not going to do that for this one. All right, so we're given a function. Piecewise, there are 3 pieces. So you really got to pay attention to what your input is. It says find the points at which the following function is discontinuous. So they're asking, is it discontinuous at x equals -4? Is it discontinuous at x equals -2, or neither? It might actually be continuous at both those values. All right, so let me write down our function. So again, piecewise, oops, better marker, sorry. So f of x could be one of three outputs, depending on what your input is. So the top piece was -2 times x squared plus 1. But that was only if x was less than or equal to -4. And then you got 3x minus 19 in this middle piece, and that's if x is a value greater than -4, but at the same time less than or equal to -2. All right. And then the third piece here, the output is 3x squared minus 37. And this is only if the value of x is greater than -2. All right. So let's take a look around, x equals -4. Start with that. So remember, the first condition is, does the function, have a value at -4? Now here, x equals -4. I'm plugging in -4, so I'm in this top piece. See, I'm going to this expression when x is less than or equal to -4. So I'll be plugging into that top piece, -2 times, -4 squared plus 1. And, -4 squared is positive 16. Times -2 is -32, plus 1 is -31. All right. So if I were looking at a picture, trying to draw a graph of this function up here, here's -4 for x, and then the output, would be -31, and this would be a point on my graph. This would be a nice solid point, or -4, -31. All right, now I'd like to know, does the graph approach that location on both sides? Because if it does, then it's continuous there. Now, being piecewise and defined differently when you're to less than -4 and when you're greater than -4, I'm going to do the left side and right side limits separately. So the limit as x approaches -4 from the left. Now this means, x is less than -4, so that means I'm on the top piece. I'm going into this top expression, because this is where x is smaller than -4. So I'm plugging into this. This is one where I can just apply the limit laws and do a direct substitution here, because this is a polynomial. These are all polynomials, so I'm going to be able to just do a direct substitution. And this is -31. Okay, plugging -4 in. So the graph will be approaching. Now, I don't know how it does, but I know it will be. Graph will approach that location, the output of -31, from the left of -4. But hopefully it does the same thing from the right side. So the limit as x approaches -4 from the right. Now when x approaches -4 from the right, that means I'm plugging in values greater than -4, but still close, So this bottom piece, yeah, these are all greater than -4, but they're not close to -4, right? The ones that get you close to -4 are here, where I'm just greater than -4 in this part. So I'm going into this middle piece, the 3x minus 19 expression. And, again, -4 is part of the domain here, so I can just apply the limit laws and make a direct substitution. This would just be 3 times -4 and then minus 19. Well, that's -12 minus 19. That is -31. So from the right side, again, I know it'll be a line, but I'm just drawing a rough idea as to what the graph is doing. So from the left, from the right, and at x equals 4, -4, they're all the value -31, right? So since all these are the same, f is continuous at x equals -4. Right, so that's not going to be my answer. Right, one of the answers was, choices was f is discontinuous at -4. That is not happening. So now how about this down here? How about at x equals, the other value they mentioned was -2. The other number that shows up in these conditions up here. So first, what's the value of f at -2? So this is when x equals -2. So that'd be this piece here. Right, x equals -2 is part of this, so I'm plugging into this, and that'd be 3 times -2, minus 19. So that's -6. Minus 19 would be -25. All right, so here's what's happening. So at -2, here's -25 would be above -31. So this point is on the graph. Right, this point here, there's -2, -25. That is a location on this graph. Now the question again is, will the graph approach this location from both sides of -2? So I'll take the limit as x approaches, -2 from the left. And if I'm approaching -2 from the left, remember this means I'm plugging in values less than -2, but close to -2. So I'm on this second piece again. So the expression I'm going into here is 3x minus 19. So this is still -25 again. All right, so from the left side, the graph would be, I know this isn't the graph, right? This isn't the graph. I'm just telling you what's happening. So from the left side, the graph would be approaching this point with the y value of -25. So far, so good. And then the right side, limit as x approaches -2 from the right. This means I'm plugging in values greater than -2, so I'm down here in this last piece. 3x squared, minus 20, minus 37. And being another polynomial, right, -2 is in the domain, and I can use the limit laws and just apply direct substitution here. This would be 3 times -2 squared minus 37. That's, 12, 4 times 3. And then 12 minus 37 is -25. So we're continuous at -2 as well. Right, since all these were the same, the left side limit, the right side limit, and the value at -2 were all the same. So f is, continuous at x equals -2. So that's not going to be my answer either. So it was actually neither, right? All these choices, it's not discontinuous at -4. It's not discontinuous at -2, right? So none of the above. This function is actually continuous everywhere. All right. All right, so another one with a graph, very nice. So look at the graph of this function, and which of the following statements about the continuity of f at x equals -6 are true? So here's what happens at -6. Now see, there's a solid point where x equals -6. So the value of the function exists and is 4. Right, the point -6 comma 4 is actually on the graph. The left side limit is 0. The right side limit is 4. So this is where the problem is, right? The two-sided limit doesn't exist. So you're going to get another one of those jump discontinuities. So down here, because it's not defined at -6, it's defined, right? The value at -6 is 4. So f of -6 exists, right? That was 4. But f is not continuous at -6 because the two-sided limit does not exist. So that same option we saw in a previous problem, right? Right, the two-sided limit doesn't exist at -6, so it can't be continuous there. All right, so this one's pretty similar looking to the very first question I went over. So I'm just gonna say this, right? It's very similar to the first one. So they're asking, is this piecewise defined function we're given here, is it continuous at x equals 3? So if I were to plug in 3, right, that's in the top piece, because you got x equals 3 up there. Plug in 3 to the top piece, that'd be the square root of 6. And if you did the left limit, you'd also be in the top piece. The limit as x approaches 3 from the left would be the square root of 6 again. And then for the right side limit, you'd be in this bottom piece, because x is greater than 3. And again, being a polynomial, I can just use the limit laws and basically just boil down to a direct substitution. The limit as x approaches 3 from the right of this function would be 9 plus 15, that's 24, minus 24 is 0, plus the square root of 6. So the value at 3 is square root of 6. The left side limit is the square root of 6. The right side limit is the square root of 6. So since all those are the same, the graph would be connected at 3 comma square root of 6, that point. So f is continuous at 3. So that objective's done. So another one where I'll just, you can plug, here's another piecewise defined function. They're asking about, is it continuous or discontinuous at -2? And if it's discontinuous, what kind do you have? So this is, again, pretty similar to a problem we saw earlier. So the value at -2 exists. When x equals -2, you go into this top piece. 2 minus 3 times -2, that's 2 plus 6, which is 8. And then the left side limit would also be 8 because you're still in that top piece. But the right side limit, if you're going to the right of -2, you're in this bottom piece. That's where x is greater than -2. And being a polynomial, again, I can just substitute. -2 squared is 4, times 3 is 12. And then, plus 4, -2 times -2. So you got 12, plus 4 is 16, plus 2 is 18. Okay, so, the value exists at -2, it's, 8. The left side limit, also 8, but the right side limit would be 18. So the left side limit exists, it's 8. The right side limit exists, it's 18, but they're not the same, right? So remember that was that was the jump discontinuity again, right? Like I said, this is very similar to a problem we saw earlier. Another graph. So which of the following statements are true? So this is all about at x equals 0. So if you look at x equals 0, see how the left side limit exists? It's -2. The right side limit exists, and it's 6. The value at 0 is 6, right? There's a solid point. So it's a jump discontinuity, right? Again, left side exists, right side exists, but they're not the same location, right? So the two-sided limit doesn't exist. And hopefully you can see from the picture that there's definitely a jump here at x equals 0. So jump discontinuity. All right, so that objective's done. All right, so another continuity of a piecewise defined function. Now this is a little different. This is something we haven't seen, so I'll write this one out. So it has to find the value or values of k that makes the given function continuous. And if there are multiple answers, you got to separate them with a comma. If there's no solution, you enter this empty set symbol as an answer and enter an exact value or values, right? So no crazy decimals or anything like that. Just enter exact values. Okay, so here's this piecewise defined function. We have f of x equals, and then in the top piece, there's the square root of k times x, right? We're trying to find the value or values of k. If they exist, that will make this thing continuous. If 0 is less than or equal to x is less than or equal, just less than, sorry, not equal to 2. And then the second piece, the output is 4x plus 17. But this is only the output if x is between 2 and 6, including both, right? So the only place this could possibly be discontinuous is at 2, right? That's where the pieces change. So I'm going to say what value and or values, there may be more than one, of k will make f of x continuous at x equals 2. Right, that's the question. Everywhere else is fine. It's just where do the pieces change? That's the only possible, those are the only possible places where a piecewise defined function might be discontinuous. Of course, if they had an expression that was discontinuous somewhere in that piece, it could be discontinuous in between too, but like for most of these, where the value where the piece changes is what you're going to focus on. All right, so first off, let's plug in 2. All right, so what's f of 2? Now, when x equals 2, you're in this bottom piece, right? This top piece does not have x equals 2 as an input. So I'm plugging into the bottom rule here, 4 times 2 plus 17. That's 8 plus 17, that's positive 25. So that's the value of f at 2. So 225, right, would be a solid point. That would actually be a location on the graph. So now what I want to happen to be continuous at this point is for the left side of the graph and the right side of the graph to approach that location. Now I can already tell you that the right side limit, so the limit as x approaches 2 from the right, is 25, right? Because when x is approaching 2 from the right, it means x is greater than 2. That's in this piece here, right? We're greater than 2, bigger than 2, so I'm going into 4x plus 17. And it's one of those where I could just do a direct substitution and apply the limit laws and get 25 here. So I know that, on the right side, the graph is approaching my location. So we want to make this continuous at this point. We want the left side limit as x approaches, 2, sorry, negative 2 from the left, well, minus there. We want the limit as x approaches 2 from the left of this function to be equal to 25 as well. All right, that will connect everything. All right, so this here, and when x is smaller than 2, I'd be in this top piece, right? So just kind of plug in 2 for x there. You get the square root of 2k. Right? So this side, you got the square root of 2k. And there's your left side limit. And I need this to be equal to 25. And now I have an equation where I can then solve for k. So I remember how to solve, so equations with roots. I would square both sides. So that's 2k on the left equals, and then over here 25 squared is 625, and then divided by 2. So k must be 625, divided by 2, and that doesn't simplify any further. So this is the value that k must be for these two pieces to connect at that point and be, continuous at x equals 2. All right, and I'll verify that. I'll show you in Desmos that they actually connect. So again, I'll just graph the one piece at a time. So that top piece was the square root of kx, but we said that k was 625 divided by 2, times x. But I only want to look at this from 0 to 2, so 0 less than or equal to x less than 2. And I'll change the color of that. I'll just wait till everything's graphed and then change the color. Yeah, see that? See, there's, it's approaching. Now it's not there, but it's getting closer and closer to the point 225 from the left. And we'll see that from when I put in the right piece. Here's 4x in parentheses. There's multiple terms, 4x plus 17. But I don't want to see that entire line, right? So curly braces. I just want to see the part of it that's, where x is between 2 and 6. And change the color. Make them both red or something. So you see how from the right approaching 225, and then from the left approaching that same location, right? That point 225, and I'll put it here and label it. See how it's being connected? There's definitely continuity there, but only when k is, 625 divided by 2. And that's it. So I'm entering that 625 divided by 2. There's the value of k. That will make that continuous. All right. All right, so this is pretty similar to the last example. So I'm not going to write this one out. Just say what I'm doing. So the only place, that this is a square root with, of kx in the top, negative 3x plus 13. The only place this could possibly be discontinuous is at 3. Now the value at 3 would be 4, right? When I plug in, I'm in the bottom piece here. If I plug in 3 for x, that'd be negative 9 plus 13, that'd be a value of 4. And the right side limit would also be 4, right? That's on the bottom piece again. So I want the left side limit to also be 4. So if I have x approach 3 in the top piece, that gives me the square root of 3k. So I'd have the square root of 3k equal to 4. And then solve for k. Square both sides, you'd have 3k equals 16, and then divide by 3. So 16 divided by 3 is the value that k must be to have these two pieces connect and be continuous at x equals 3. You can write out everything I just said if you want, but very similar to the previous question. All right, so now all those objectives are done, right, from that one section called, continuity at a point. So you see that here. So now I'm going to be in this continuity over an interval and the intermediate value theorem for the last part of this video. All right, so we're asked to determine where an algebraic function is continuous. So remember that graph from earlier in the video where they asked us to, state what interval or intervals over which a function was continuous. So you just have to eliminate any points where there are discontinuities. So I'll write this up now. Your algebraic functions. So all the class. So if you remember your pre-calculus and college algebra courses from before, trigonometry, Your algebraic functions, these were your polynomials, rationals, radicals, right? Things with roots, radicals. Algebraic functions, trigonometric functions. Also with inverse trig, right? Inverse are included there. Exponential functions, logger. I'm kind of getting ahead of myself. They don't really bring these up till a later section, but your exponential functions, your logarithmic functions. All right, pretty much. I'm sure there's more I'm forgetting here, but so your polynomials, rationals, radicals, trig, inverse trig, exponential, logarithmic. Yeah, it might be the hyperbolic. You probably, I don't know if you studied the hyperbolic functions. It doesn't matter. All these classes of functions that you should have studied in a pre-calculus course, these will be continuous wherever they are defined. So they're continuous on their domains. All right, so remember the domain was any value you could plug in and get an actual output, a real number output. So this example here, right, we're given this function, and it's one of these rational functions, right? So algebraic. You got negative 3x squared, minus x minus 2 in the numerator, and x squared plus 3x plus 2 in the denominator. So if you were to just, I don't really care so much when I'm going and thinking about the domain. Remember, you can't divide by 0. There were certain trig functions, tangent, cotangent, secant, cosecant. There were certain values that weren't in the domains of those. Now, everything was in the domain of an exponential. Remember, you could only take logarithms of positive numbers. Even roots of non-negative numbers and so on, stuff like that. You're trying to think of what you could plug in and get a real number output that was defined. So when it comes to rational functions, and I'm going about stating the domain, the numerator, yeah, you could probably factor it, but I'm not gonna. Because all that matters is what makes the denominator 0, right? This is x plus 2 times x plus 1 down here. So f will be continuous on interval, and it's basically everywhere except -2 and -1, right? Because if x equals -2, at x equals -1, this is undefined. You're dividing by 0. So you're going to have, at these points, you're going to have either an infinite discontinuity or a removable discontinuity. Probably not a jump here, but still, at either of these points, these values, you'll have a discontinuity. So you'll be continuous everywhere else. So that's from negative infinity, up to -2, but then you have a discontinuity at -2, so parentheses there. It says if there are multiple intervals in the problem that you separate them with the union symbol or a comma. I think a comma would be faster, so a comma here or the union symbol. Then after -2, you'll be continuous, from -2 to -1, but again, not -1, so parentheses there. And then from -1 onward, right? So from -1 to positive infinity. So here's what I'm going to be entering. And again, that's just the domain of this function, right? So once again, all the nice classes of functions you should have learned about in pre-calculus, they will be continuous wherever they are defined, continuous on their domains. So here, and entering an interval notation, negative infinity. So that's here in the menu, negative infinity up to -2, right? But not at -2. Now let's do a comma, right? It says separate with a union symbol or a comma. I don't see the union symbol here. If you want to find the union symbol, though, it's in sets. Right, there's union, but you know, I already put the comma. So then parentheses, -2 to -1, comma, and then from -1 to infinity, which is also here, all right? And that should be good, right? These are the intervals over which this function is continuous. And if you'd like to go to Desmos, make a graph of this, you'll see that at -2 and -1, there are discontinuities. So it's continuous everywhere else. Right. Okay. All right, so now we're getting to the intermediate value theorem. So I state what that is. So the intermediate value theorem. So this states that if, all right, so if the following is true, then then something's got to happen. So if we have a function, so say f of x, if f of x is continuous on some closed interval, so on an interval from x equals a to x equals b, notice the brackets here. That means they're included, so add x equals a to everything, and then everything in between, and then add x equals b. And the value of f of a is not equal the value of f of b. Right? So the value at each end is different. So graphically speaking, here's what's going on in this hypothesis. So x equals a to x equals b, and then say the value of f at a is here. Right? So here's the value of f at a on the left end, and as long as the value of f at b is different, right? So it could be higher, could be lower. I'll just make it higher. So here's f at b. So I got that. That's this condition. So the value at both ends is different. And the first condition was the graph is continuous. So now it doesn't have to be a straight line, right? But as long as I don't lift my pencil, so I could have a graph that does this, goes all sorts of wavy on me, but it still is drawn without any breaks or holes or jumps in it, right? So there's continuous, there's one example of there's y equals f of x in green there. So if these two conditions are met, like in my picture, then every value between those two outputs at the ends, so every value that's strictly between, okay, between f of a and f of b. So we're talking these values here. So all these values in between, just the ones between f of a and f of b. So every value between f of a and f of b has at least one x value between a and b that maps to it. Has at least one x value between a and b that maps to it. Okay, so for instance, right, so again, take any value between the y values at the ends. Take any value between f of a and f of b, say this value here. I'll call it, let's see, I've used A and B. I'll call this C. As long as it's between these two, there should be, and if you go to the graph, right, there's this point and this point, and even this point over here. There should be at least one value on the x-axis. There's one, there's two, there's three that give me that output, that map to that output. And that should work for any value in between those values at the ends, f of a and f of b. There's one more example here. So here's another value, right? Again, between f of a, I'll call it d. Go across and see, hey, there's this point, and that x value is between a and b. And then there's this point, and that x value is between a and b, and so on, right? You'll always be able to find at least one x value between a and b down here that map to your value, between f of a and f of b. But these conditions have to be met, though, right? These two conditions must be met in order for us to guarantee that this will happen, right? Because if they're not, say it's not continuous. So here's A, here's B. So say this is f of a, say the second condition holds, but not the first one. So say here's f of a, here's f of b, and they're different outputs. Now, what if there's a discontinuity in here? Maybe maybe it does this, and then there's like a hole here or something, and then we do that. Say there's a discontinuity. Well, then you see how not every value in between f of a and f of b would be mapped to. All right, there'd be this value here that, oh, that's a missing point. There's no question marks down here. There's no x value between a and b that would give me that y value. All right, so that's missing. So it's got to be continuous. All right, so that's the intermediate value theorem. So let's see how they're asking us to use it. So back on the question. Understand and apply, the intermediate value theorem. So we're told the function f of x is continuous from x equals -9 to x equals -3, right? On the interval, the closed interval from -9 to -3. So the table below gives some of its values. What is the minimum number of zeros? So those are x-intercepts, right? You might recall that from algebra or pre-calc, right? When they say what the zero of a function, those are what x values give you an output of 0, right? So x-intercepts. What is the minimum number of zeros that is guaranteed, that the function is guaranteed to have in between -9 and 3, -3 by the intermediate value theorem? Okay, so I'll actually draw these up, plot these points. So we're told this function is, continuous on this interval from x equals -9 to x equals -3. And so here's x equals -9. And I'll put on all of it. Now I got -8 for an input, -7, -6, -5, -4. Sorry, this isn't great. -3. Right. Sorry, I should have the whatever. All right, now, and the value of f at -9 is not the same as the value of f at -3. Right. So f at -9 is +9. So we got this point. It should be on the graph, -9, 9. They're saying at -8 needs to be 4. -7, also 4. -6 has an output of -4. So I'm just plotting the points that are given to me in the table. -5, -2, -4, -7, and then -3, -9. So, and this shouldn't, be whatever. Now, being continuous. Now, I'm just going to make these straight segments, but being continuous over this interval means I can draw a graph. Now, this might not be the exact look of it, but I know it's got to be continuous, right? So we have to have these all connected without lifting the pencil, right? That is one example of what f could be, right? That is a continuous function over this interval. So they're asking, how many x-intercepts are guaranteed? Or what's the smallest amount? What's the minimum number of x-intercepts? How many zeros are guaranteed? Right, zeros, x-intercepts are, guaranteed by the intermediate value theorem here, right? The conditions are met, so I can apply it. I'm just going to put I, B, T for intermediate value theorem. Well, if you just draw little straight segments like this, right, the only thing that's guaranteed is that there has to be a zero between -7 and -6. There could be other ones, right? Like between -8 and -7 here, it could have dipped all the way down here and come back up. Or between here and here, it could have gone up and then came back down. But, we don't know that based on the information that was given. All we can guarantee is that, hey, the value is positive to the left of -7, positive at -7, and the value is negative at -6. And then because it's continuous, right, we're told it's continuous, there has to be a place in between where the graph crosses the x-axis. Has to be. And that's the only time you get this positive on one side, negative on the other thing going on. So only one is guaranteed. There may be more, right? There may have been more x-intercepts. This might not be the graph of f, but I guarantee you it's going to hit the x-axis at least once. So looking at the table here, right, it only goes from positive to negative one time. Now, if it ever went from negative back to positive, then I would say, it would have to cross the x-axis again. Yeah, but we only are guaranteed 1 0 here. So I'm going to put in f has a minimum of 1 zeros. So yeah, you're really looking for there, if it's continuous, you're looking for where does it go from being positive to being negative or being negative to being positive. Because that's where you're guaranteed to have an x-intercept. So another intermediate value theorem problem. All right, so here, if f is continuous, from x equals 3 to x equals 5, on the closed interval from 3 to 5, and then f of 3 is positive and f of 5 is positive, can we use the intermediate value theorem to conclude that f has a 0 in between 3 and 5? And so I'll draw up the information they're given here. It's a little different question. So they're saying this function is, continuous on this interval from, 3 to 5. So here's x equals 3, x equals 5, and we're told that f of 3 and f of 5 are both positive. I'll just make them so that they're different. So here's f of 3, positive, and then say f of 5 is something else, right? We're not told exactly what the values are. So I'm just going to say they're different, and here's f of 5, but they are both positive, right? So, and it's continuous. Now, question is, can we use the theorem, can we guarantee that f has an x-intercept? right, has a 0 in this in between 3 and 5. Well, look, I mean, let's do a straight segment again. You don't know what f looks like. F could look like this. Just be there. That's a continuous function. That's continuous from 3 to 5. No breaks, no holes, no jumps, no gaps. And, the value at one end different than the value at the other. So, the intermediate value theorem would say that every value in between here and here, between f of 3 and f of 5, is mapped to, right? There's an x value that goes there. But notice how, this particular one doesn't cross the x-axis. If the value at both ends is positive, you can't guarantee that the graph has an x-intercept. Now, it could have done this. All right, here's 3, here's 5. Say f of 3 is this and f of 5 is that. Now, the graph could have done this. It could have dipped down and then come back up, and then you had some x-intercepts. But that's not guaranteed. Right? You don't know that. What if it was just a straight segment like I had up here? Right? So the answer is no. Right? I can't use the theorem to say, oh yeah, there's got to be an x-intercept in here, right? No, the only thing that the theorem would state is that every positive value in between f of 3 and 5 must have an x value that goes to it. That's all it would say. And, none of those are 0. So no, the intermediate value theorem does not guarantee that f has a 0 in the interval. Now, if it was positive at 3 and negative at 5, less than 0, then we have to cross the x-axis. So this is just a simple limit law. The composite function theorem is another limit law where you can basically pass a limit inside composite functions inside, so like I mentioned earlier, all these functions and compositions of them, all right, the algebraic functions, trig, inverse trig, exponential, logarithmic, right, all these things that you saw pre-calculus or college algebra, they should be continuous wherever they are defined. So if you have a crazy looking function like this, as long as it's defined at the value your limit's going to, you can just, do a direct substitution to state the limit to find the limiting value. So for example, here, we have the limit. The limit as x approaches pi over 3 of, and then this, function with a bunch of trig stuff in it, you got the sine of, and then inside this sine function 3 times the square root of 2 times x divided by 2 pi, and then minus now this is still inside, the parentheses didn't close, so this is still inside. You got minus the cosine of 3 times x divided by 4. That's closed, and then plus pi over 2. And now the parentheses for the sine are closed, and then there's the whole thing. So again, these are sines and cosines, and you got polynomial terms in here. I mentioned earlier, all these things, polynomials, rationals, radicals, trigs, inverse trigs, all that stuff. If you plug it in and it's defined, there's your limit, right? These functions are continuous on their domains, continuous wherever they are defined. So I should just be able to find this limit by plugging in the number. So it should be equivalent to the sine of, 3 times the square root of 2 times pi over 3 divided by 2 pi. Then, still inside the sine here, minus the cosine of 3 times, pi over 3 divided by 4. And then plus pi over 2, all still inside this sine here. So I'm just doing a direct substitution. being that these are sines and cosines and polynomial terms inside here. These are defined everywhere, so continuous everywhere. I can plug this in. Now, if there were like tangents or other types of functions that might be undefined, I'd have to do a little more thinking, but we're good here. Now we got some cancellations going on, right? The 3's would cancel here, and then so would the pi's. So this ends up being square root of 2 over 2, and then 3's cancel here. So this is cosine of pi over 4. So I'll just do one little simplification at a time here. So this is the sine of, and this all with the cancellations becomes square root of 2 divided by 2 minus the cosine of, this just becomes pi over 4, and then plus pi over 2, right, all inside the sine. You may recall the cosine of pi over 4 was also the square root of 2 divided by 2. So then inside this sine, I have the square root of 2 over 2 minus the square root of 2 over 2. That's 0. So I'm just left with the pi over 2 in there. So this ends up being the sine of pi over 2, which is 0. No, 1. 1. Ugh. Sorry, it's been a long video. Remember, sine of 90 degrees, sine of pi over 2 radians was 1. So this limit is 1. And you could go to Desmos and make a table of this, a graph of this, and see that as x approaches pi over 3 from both sides, you'll approach the point pi over 3 comma 1. Right? It has a limiting value of 1. So I asked to enter an exact answer, which is just the number 1. Great. Right. Same deal, right? Notice this is one of those exponential functions, e raised to a power with a variable, right? And again, your exponential functions, logarithmic, whatever, they're continuous on their domains. So as long as things are defined, you can just do a direct substitution and evaluate the limit. If for some reason it's not undefined, if for some reason it's undefined at the value, right, then you gotta do something else to possibly evaluate the limit. But we should be good with direct substitution for all the problems that I'm going to see here, right? I don't think they're gonna go too difficult on me in this introductory section. So e raised to the negative 2x plus 4/9 power, right? This is all in the power here. So I'm just gonna plug in the negative half. This is equal to e to negative 2 times negative half, because again x is approaching negative half, plus 4/9, and then just simplify that power a bit. This is e to the positive 1, plus 4/9, and when you add things, you need a common denominator, so that's 9/9 plus 4/9. This would be e to the 13/9 power, and that's all they want. They just said, write an exact answer. Don't punch this in a calculator or anything and round to some crazy amount of decimals. Right? Just enter an exact answer. So e raised to the 13/9 power. Just a direct substitution again. All right, so another one where I mentioned this earlier, multiple times now, right? All these algebraic functions are continuous wherever they are defined. So we're given this here, of x equals, the square root of some quadratic, and we're asked to state the intervals over which this is continuous. Yeah. So I need to know where it's defined. And it'll be continuous wherever it's defined. So our function, the square root of negative 3x squared minus 12x minus 12. Okay. This is an even root, right? Square root, even root. So that means, we're only going to be defined wherever the expression inside is non-negative, right? So this expression inside must be, non-negative. In other words, this negative 3x squared minus 12x minus 12 must be greater than or equal to 0, and we'll solve this and see if this has any solutions on the real number line. Okay, so you might recall, again, I'm hoping this is a refresher, but from algebra class, pre-calc, how to solve quadratic inequalities. All right, if you were to look at the graph, this is just one way to go about it. If you were to graph y equals negative 3x squared, minus 12x minus 12, that's going to be some parabola opening down, right? The lead coefficient is negative. So I'm going to find the x-intercepts. So where is this equal to 0 first? Multiply. I'm going to divide everything by negative 3. So that's x squared plus 4x plus 4 equals 0. And then this is just x plus 2 squared. So yeah, the only solution is negative 2. So it's, negative 2. You got the point negative 2, 0. And it would be a parabola opening down. So you got, 0, negative 12 would be the y-intercept. And that would be the vertex, right? Remember when there's only one x-intercept. So we're trying to find values where this is greater than or equal to 0. The only time it's equal to 0 is when x is, well, negative 2. I know I put negative 2 over here, I'm sorry. But negative 2 is where it's 0, and then everywhere else, so sorry, I guess this should be over here, the y-intercept. But everywhere else, this expression is less than 0, right? You have y values less than 0. So the domain of f is just x equals 2, or negative 2. Right? That's it. It's got a single value. And watch. All right, so I'll go to Desmos. I'm gonna go enter this expression, and we're gonna see the only point on this graph will be at negative 2, 0, because you have the square root of 0. So here, f of x equals, the square root of negative 3x squared minus 12x, then minus 12. Now, if I go to a table for this, you'll see negative 2, 0. See, it's just a single point. Everywhere else, no matter what you plug in, no matter what else you plug in, you see it's undefined, undefined. I could put in anything I want. Negative 81, 0.78, 1.2656. Doesn't matter. The only value that's in the domain is negative 2, right? So I'll draw this graph. So the graph of this function is just this. So here's a negative 2. And again, when x is negative 2, this becomes the square root of 0. So it's just this one point. That is it. Now, if the domain only contains one value, then you're not continuous there. Right? F of negative 2 exists, right? F of negative 2 is 0, but remember the other condition for continuity? The limit as x approaches negative 2 does not exist, right? Because here you're plugging in values that are not -2. But notice how there's no graph to the left of -2. There's no graph to the right of -2. So the left side limit doesn't exist. You can't talk about it. You can't even plug these values in. The right side limit doesn't exist. Again, you can't really talk about it because, there's nothing there. So even though there is a value where it's defined, if it's just a single value like this, the two-sided limit there, doesn't exist. So f is, discontinuous also at x equals -2, right? So it's a little caveat, a little exception to the statement earlier about being continuous on the domains, right? If the domain has, this singular value, not going to be continuous, right? Discontinuous at x equals -2. And of course, it's not defined anywhere else. So overall, f is discontinuous everywhere. They would say discontinuous everywhere for all x. There is no point where this is continuous by definition using those three conditions of continuity. So back in the problem. So you see they have that little, this kind of gave it away that might happen. See the part of the instructions where it says, if the function is not continuous anywhere, enter your answer as this empty set, and that's what we discovered. So now that's not showing up here. That should be in sets. There's this empty set symbol. Okay. And again, read through the answer explanations. They talk about it, right? X being -2. That's the only value in the domain. There's the graph of it. But it's not defined outside that. See, the two-sided limit doesn't exist. Can't be continuous if the two-sided limit doesn't exist. Or one-sided. You might be continuous from the left or the right. That is also a thing. Be careful. All right, so another one where we're just kind of doing a substitution. Remember inverse cotangent? Inverse cotangent was defined for all real numbers. Okay, you can have anything in inverse cotangent. Now, the only place this would be undefined would be where this denominator was 0. So at -4 or at -2, right? Because this is x plus 4 times x plus 2. But this value we're approaching is not -4 or -2, so we're okay to just plug it in. All right, so I'm just going to actually go to Desmos here and type this in. I don't feel like writing all this out. So I'm going to enter this expression, this inverse cotangent of all this, and just, have it substitute -8/3. All right, so I'll call it f of x equals, you got arc cotangent, right? Remember, arc cotangent was inverse cotangent. You throw arc in front of the trig functions, and that was the inverse trig function. Then we had, -2x squared minus 14x minus 24 in the numerator. I already forgot. 14x minus 24. And then the x squared plus 6x plus 8 in the denominator. All right. Yes. Okay. So there's f of x, and then we're just plugging in, -8/3. Ooh, and that's not a nice number, is it? It does want an exact answer. All right, so I'm gonna have to actually write this out. I think, okay. So when you're doing inverse cotangent, if they gave you a value that gives you a special number, remember cotangents and tangents, the special numbers were 1 and -1 and square root of 3/3 and square root of 3. I feel like this is square root of 3/3. Let me just double check. Square root of 3 divided by 3. It is not. Okay. Alright, so I actually have to go through this. I apologize. I thought I could get something nice out of this from Desmos, but let's go and actually plug this in. Let's make sure I entered that correctly. Inverse cotangent, -8/3. All right. Okay. So looks like I got to do this by hand. All right. So we have the limit as x approaches, -8/3 of the inverse cotangent of -2 times x squared minus 14x minus 24 divided by x squared plus 6x plus 8. And instead of plugging it all in right now, I am going to see if we can simplify this fraction here first. Now, from the numerator, I can factor out a -2, and then we'd have x squared plus 7x plus 12. Yeah, there is some simplification that we can do. And then x, I said earlier, x squared plus 6x plus 8 is x plus 4 times x plus 2. And, this numerator, x squared plus 7x plus 12 factors to x plus 4 times x plus 3. Okay, so the x plus 4s would cancel. So this is the inverse cotangent of, you have -2 times x plus 3 left in the numerator, and then just this factor of x plus 2 now down here. All right, so this will be nicer. And then I'm just putting, -8/3 in for x. So we get our limit equal to the inverse cotangent of -2 times, and then, -8/3 plus 3 divided by, and then, -8/3 plus 2. And we got a nice complex fraction going on here. So this is inverse cotangent of -2 times, now when you add or subtract stuff, need a common denominator. 3 is 9/3. So -8/3 plus 9/3, that's +1/3 divided by, and then again, -8/3 plus 6 is 2/3. Oh, you know what? I was silly. I shouldn't have put in the value. When you do inverse cotangent, you're getting special angles back. Not special, not the output. Sorry. So I should have been checking for pi/4, pi/3, pi/6. Silly me. My apologies. But you can see how down here, -8/3 plus 6/3 is -2/3. And you have -2/3 divided by -2/3. That's 1. So this is the inverse cotangent of 1, which was positive pi/4, right? That had an angle. That angle had a cotangent of 1. Yeah, and if you go back, sorry about that. Yeah, I should have thought more about inverse cotangent. Yeah, the special values that show up are angle measures, pi/4. Yeah, that's the value I was looking for. All right, so when all's said and done here, this is pi symbol down here, pi divided by 4. Great, great. All right, so this is one where I can just plug in the number again, right? Just do a direct substitution, applying the limit laws. As long as it's not undefined, it should be good. All right, so I'm just going to do this out loud here. This is pretty similar to a problem earlier. So when I plug in x approaches a half, so this power up here, you approach 1/2 to the 4th, which is 1/16. All right, then 1/16 and 2/9. I'm going to see what happens when I just enter. It says enter an exact answer. It doesn't say anything about simplifying it, so I'm going to do this. Got 2 times e raised to the, and then 1/16 plus 2/9, all in the power there. And that's equivalent to the correct value. Let's see. Look at that. Okay. Now you could put the 1/16 and 2/9 together and get, 41 1/44, getting a common denominator of 144 like they do. But yeah, they said enter an exact answer. They didn't say anything about simplifying it. So keep that in mind. Okay, all right, so that objective's done. So here's another one where I'm asked to, state the interval or intervals over which, this function is continuous. Right, so it's got an even root and it's got something in a denominator, right? So I have to really, really, really pay attention here. So again, this is one of those things where a function will be continuous on its domain, unless, like we saw in the previous problem in this objective, unless the value, there's only one value in the domain or no values in the domain. All right, so our function is the square root of 1 divided by 2x squared plus 14x plus 24. So again, we have an even root. So this expression in here, 1 over 2x squared plus 14x plus 24 must be greater than or equal to 0, but also, right, that denominator can't be 0. So we got to make sure to exclude any value there. Now 2x squared, let's look at that on its own. 2x squared plus 14x plus 24. Now I can pull a 2 out of that. That'd be 2 times the quantity x squared plus 7x plus 12. And that's 2 times, x plus 3 times x plus 4. So yeah, the values that make it 0 are -3 and -4, right? So -3 and -4 can't belong to the domain here. There's definitely a discontinuity at those values. And then you may recall, this other method for solving rational inequalities. I put a number line, here's values of x, here's the expression, where the denominator is nice and factored. And at x equals -4 and at x equals -3, this is undefined. I'll just put UND for undefined. So now we care about where is this expression positive or equal to 0. Well, it's not going to be equal to 0 ever, right? The numerator is always 1. So where is it positive, right? We just want to know where is it positive. Now to the left of -4, say I plugged in -5, -6 or something. You'd have a negative there, negative there. So it'd be positive overall. Right, you'd have a 1 divided by positive times negative if x were -5. So positive overall. So these values from -infinity up to -4, but not including -4, f will be continuous. F is defined, so will be continuous on that interval. Then between -4 and -3, say I chose like -3.5, then this would be negative, this would be positive, this factor. So you'd have a negative overall, so less than 0. So this would be undefined between -4 and 3. And then to the right of 3, say I chose 0, then this will all be positive. You have a positive overall. So union from -3 to infinity. So these are the values for which that function is defined. So everywhere where it's, again, not defined, you'll consider it, discontinuous. There you go. It's continuous everywhere else, continuous on its domain. If its domain has, more than one value, which this does. So back here, enter. Now I actually have some intervals to enter, and it does say separate them with a union symbol or a comma. I'll just do the comma again. So this function is going to be continuous, from -infinity up to -4, comma, and then, not between -4 and 3, and then from -3 to positive infinity, right, on its domain. Great. And again, read through the answer explanations. They go through all that. All right. All right, so this is very similar. Very, very similar to the last one. All right, but so again, I'll write it out. This should be relatively quick because it's so similar to the last one. So our function, again, big square root of 1 over 2x squared plus 6x minus 8. So I'm going to take a look at the denominator there. 2x squared plus 6x minus 8. I could factor a 2 out of this. Then we'd have x squared plus 3x minus 4. And then that would factor to x plus 4 times x minus 1, right? So again, that can't be 0. So that means x cannot be negative 4 or positive 1. And then what we need is this expression inside here. We want to find where is this greater than or equal to 0. Well, it's not going to be equal to 0 ever, right? The numerator is always 1. So we want to know where it's greater than 0. So I'm going to have this number line. We know at x equals negative 4 and x equals 1, the expression is undefined. Little UNDs there. And here's 1 over the factored version of the denominator. And then to the left of negative 4, say I pick like negative 5 or something. This will be negative, this will be negative, so positive overall. So again, we have f is continuous, right, where it's defined on these values from negative infinity up to negative 4. And then, not in between, right? When x is 0, something between negative 4 and 1, this would be a positive number here, but that'd be negative, so it'd be negative overall, and I don't want that. And then to the right of 1, say I pick 2, everything's positive, right? So the whole expression's positive, so we do have the square root of a positive, and that's fine. So from 1 onward, the function exists and will be continuous. So from negative infinity up to negative 4, but not from negative 4 to 1, and then, beyond 1, this function will be defined and also, continuous at those values. So entering negative infinity to negative 4, and then a comma. Again, they said you could use the union symbol or a comma to separate intervals. And then the other interval it was continuous on was from positive 1 to positive infinity. All right, great. 5 of 6, one more to go. All right, so this looks like, again, more intermediate value theorem. It says find the smallest integer a such that the intermediate value theorem guarantees that this function has a 0 on the interval from negative 6 to a. All right, so if you look at the left end, negative 6. So here's the function. F of, x is, the opposite of x squared minus 6x minus 6. Now look at the left end. We're trying to go from, negative 6 to a. So I'll make a little graph here. So from negative 6 to some value a. Now they're saying what's the smallest integer? Such that, negative 6 on the left, a on the right, you're guaranteed an x-intercept, you're guaranteed to 0. Now, our polynomials are continuous everywhere. They're defined everywhere, so you don't have to worry about being continuous on whatever interval you're putting up. Now look at the left end. F of negative 6 would be, the opposite of 36, and plus 36 minus 6, so negative 6. Right, so input negative 6, output negative 6. So you got this point, and then to find the smallest value of a here, I'm just going to keep plugging in different integers until I get a positive value, right? It's negative, as a negative output at negative 6 on the left end. So I'm going to keep plugging in integers until I get a positive output, and then knowing it's continuous, that'll guarantee we have an x-intercept in between. So what's f at, negative 5? So it'll be the opposite of 25. And then, when x is negative 5, this would be plus 30, and then minus 6. So that's 5 minus 6, that's negative 1. So negative 5, negative 1. So I'm not there yet. All right, there's that point. So now I'll try negative 4. F of negative 4 is, the opposite of negative 4 squared, which is negative 16, and then plus 24, right? Negative 6 times negative 4, and then minus 6. Now 24 minus 16 is 8. Minus 6 is positive 2. There we go. There's where we're guaranteed to cross the x-axis, right? Between negative 6 and negative 5, no guarantee. But between negative 6 and negative 4, you're guaranteed by the intermediate value theorem and the fact that this is continuous and all that, right? That there will be at least one x-intercept. So the smallest integer is negative 4 that they're looking for there. All right. So this one says, on which of the following intervals does the intermediate value theorem guarantee that the piecewise function has a 0, right? So another x-intercept thing. So you got 3 intervals or none of the above. So one's from negative 5 to negative 3. The other's from negative 4 to negative 2. The other from negative 2 to 0. So notice for all of these, the values in the interval are less than 2, right? So we're in the top piece for every single one of these. This x squared plus 6x plus 7 part of the function. So they don't have any intervals here with values of x greater than 2. All right, so I'm just going to work with that top piece. In fact, I'm just going to do a Desmos and put in that expression, the x squared plus 6x plus 7, and we'll take a look at a table. So x squared plus 6x plus 7, that was that expression from the top piece. Again, all these intervals in the options here have values of x less than 2. So I'll put in negative 5 and negative 3, see, in a table. So here's negative 5, so the output is positive, and then negative 3, the output is negative. And the fact that this is a polynomial part of the piece, we're continuous here, the graph is guaranteed to have a 0 in that interval, right? So I'll check that one. Now I'll check, negative 4, negative 2. So I'm just changing these to negative 4 and negative 2. So those both have the same negative value, so you're not guaranteed by the intermediate value theorem that there's an x-intercept there, right? It's going from negative 1 to negative 1 again. So no guarantee for that one, so I'm not going to select that one. Then how about from negative 2 to 0? Well, you can see it right here. When x is negative 2, output negative 1. And when x is 0, output positive 7. So it goes from negative to positive, so you are guaranteed to have an x-intercept in between negative 2 and 0. So again, I only had to work with the top piece there. Now, if for some reason any of these had values greater than 2, then I don't have to worry about, what happens at 2. Great. And that's it. Great, wonderful. All right, so a lot of stuff there. Hopefully, watching me go through this preview helps you in some way when you're working on it on your own. And thank you very much for watching.